This is SpaceTime Series 25, Episode 134. Coming up on SpaceTime, a giant mantle plume identified on Mars, a new technique to study planetary interiors, and the Martian mega tsunami. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
A new study suggests that the Martian core could still be at least partially molten. The findings, reported in the journal Nature Astronomy, are based on the detection of what appears to be a deep mantle plume, that is, a region of liquid magma heated by the planet's core and slowly rising towards the surface. Knowing there's an active giant mantle plume beneath the Martian surface raises important questions regarding the planet and how it's evolved over time. You see, the findings contradict the long-held view that Mars, being much smaller than the Earth, has lost most if not all of its internal heat, which caused its once molten core to cool and solidify eons ago. The idea of a solid Martian core explains the lack of a global magnetic field around the red planet. The fields are generated through a geodynamo process. This involves a molten metallic outer core revolving around the solid iron inner core, in the process generating a magnetic field. On Earth, the constant shifting of tectonic plates recycle the planet's surface and make for a dynamic interior. So the absence of such processes on Mars led many scientists to think that it was indeed a dead planet, where not much has happened geologically speaking over the past 3 billion years. Now, scientists have challenged current views of Martian geodynamic evolution with this report on the discovery of what appears to be an active mantle plume pushing the surface upwards and causing earthquakes and volcanic eruptions. Put simply, the findings suggest that the red planet's deceptively quiet surface could be hiding a far more tumultuous interior than previously thought. One of the study's authors, Adrian Broquet from the University of Arizona, says the findings show multiple lines of evidence that reveal the presence of a gigantic active mantle plume on present-day Mars, a plume which is causing earthquakes, faulting, and even volcanic eruptions. A good example of a mantle plume on Earth are the chain of islands which make up Hawaii, formed as the Pacific Plate slowly drifts over a mantle hotspot. But while there's good evidence for mantle plumes being active both on Earth and Venus, this wasn't expected to be the case on the small, supposedly cold world of Mars. Scientists always thought Mars was most active geologically 3 to 4 billion years ago, shortly after it formed. And the prevailing view is that the red planet is essentially geologically dead today. Of course, there was a tremendous amount of volcanic activity early in the red planet's history, and that's evidenced by the tallest volcanoes in our solar system. These have blanketed most of the northern hemisphere in vast volcanic deposits. What little activity has occurred in recent geologic history on Mars is typically attributed to passive processes like the planet cooling and shrinking. But scientists have noted a surprising amount of geological activity in an otherwise nondescript region of Mars called the Elysian Planitia, a vast plain within the Martian northern lowlands close to the equator. Unlike other volcanic regions on Mars, which haven't seen major activity for billions of years, Elysian Planitia experienced large eruptions over the last 200 million years. In fact, previous research has found evidence in Elysian Planitia for the youngest volcanic eruptions known on Mars, which would have produced small explosions of volcanic ash as recently as 53,000 years ago, which is essentially yesterday in geologic terms. Volcanism at Elysian Planitia originates from the Cerebus fossae, a young set of fissures that stretch more than 1,000 kilometres across the Martian surface. In fact, recently NASA's Mars InSight lander found that nearly all Martian quakes emanate from this one region. Although this young volcanic and tectonic activity has been documented, the underlying cause remained unknown. On Earth, volcanism and earthquakes tend to be associated either with mantle plumes or plate tectonics, in which convection causes new crust to rise to the surface at mid-ocean ridges and older crust to subduct back into the mantle and subduction zones in a continuous cycle. Broquet says scientists know that Mars doesn't have plate tectonics. The crust is simply too thick. So instead, they investigated whether the activity seen at Cerebus fossae could be the result of a mantle plume. Mantle plumes, which can be viewed as analogous to hot blobs of wax rising in lava lamps, give away their presence on Earth through a classical sequence of events. Warm plume material pushes against the surface, uplifting and stretching the crust. Molten rock from these plumes then erupt as flood basalts, which create vast volcanic plains. When the team studied the features of Elysium Planitia, they found evidence of the same sequence of events on Mars. It appears the local surface has been uplifted by well over a kilometre, making it one of the highest regions in Mars's vast northern lowlands. And analyses of subtle variations in the Martian gravity field in this area indicate that this uplift is supported from deep within the planet, again consistent with the presence of a mantle plume. Other measurements show the floor of nearby impact craters are all tilted in the direction of the plume, and that's further evidence of the idea that something's pushed the surface up after the craters were formed. Finally, when the authors applied tectonic models to the area, they found the presence of a giant mantle plume some 4,000 kilometres wide was the only way to explain the extension responsible for forming Cerebus Fossae. Briquet says Elysium Planetary is ticking all the boxes in terms of what you'd expect to see with an active mantle plume. The problem is these findings are posing a real challenge for models used by planetary scientists who are studying thermal evolution on planets. The mantle plumes affected an area on Mars roughly the size of Australia or the continental United States. So further studies will have to find a way to account for this very large mantle plume that simply wasn't supposed to be there. Scientists used to think that NASA's Mars InSight lander touched down in one of the most geologically boring regions of Mars, a nice flat surface that was supposed to be roughly representative of the planet's lowlands. Instead, it would appear InSight's actually landed right on top of an active plume head. And the presence of an active plume will affect the interpretations of seismic data recorded by InSight, which must now take into account the fact that this region is far from normal for present-day Mars. Having an active mantle plume on Mars today is a paradigm shift for science's understanding of the planet's geological evolution. It's similar to when analyses of seismic measurements recorded during the Apollo era demonstrated that the Moon's core was also partly still molten. And it doesn't end there. The authors say these findings could also have implications for life on Mars. This region has experienced floods of liquid water recently in its geologic history, though the cause for that has remained somewhat of a mystery. But the same heat from the mantle plume that's fueling ongoing volcanic and seismic activity could also melt ice and make floods, and drive chemical reactions that could sustain life deep underground. After all, here on Earth, microbes flourish in environments just like this, and so it could all be true for Mars as well. I guess only time will tell. This is SpaceTime. Still to come, a new technique to study planetary interiors. And while on the subject of Mars, it seems the red planet experienced a massive mega tsunami. All that and more still to come on SpaceTime. Now, while we're on the subject of Mars, seismologists from the Australian National University have developed a new technique which suggests that the Martian core is some 3,620 kilometres across, somewhat smaller than the Earth's core. This new method, reported in the journal Nature Astronomy, works in the same way as an ultrasound uses sound waves to generate images of a patient's body, and importantly, requires only a single seismometer on a planet's surface in order to work. To test the idea, scientists applied the new technique to seismology readings of the red planet's interior taken by NASA's Mars InSight lander. They were able to scan the entirety of the Mars interior, confirming that the red planet does have a large core at its centre, an hypothesis only confirmed last year. Confirming the existence of a planetary core will help scientists learn more about a planet's past and evolution. It can also help scientists determine at what point in a planet's history its magnetic field formed or ceased to exist. And as we mentioned earlier, the core plays an active role in sustaining a planet's magnetic field. In the case of Mars, it could explain why, unlike the Earth, the red planet no longer has a magnetic field, which is crucial for sustaining life because it provides a protective shield against the solar wind and cosmic radiation. The modelling suggests that the Martian core is liquid, And while it's made up mostly of iron and nickel like the Earth's core, it also contains traces of lots of lighter elements like hydrogen and sulfur. And these elements can alter the ability of the core to transport heat. Using the InSight lander's single seismometer on the Martian surface, the ANU team measured specific types of seismic waves. The seismic waves, which were triggered by Marsquakes, give off a spectrum of signals or echoes that change over time as they reverberate throughout the Martian interior. These seismic waves pierce through and bounce off the Martian core. The study's authors were especially interested in the late and weaker signals that can survive hours after being emitted by quakes, meteor impacts, and other sources. See, although these late signals appear to be just noisy and useless, the similarity between them reveals the presence of a large core in the planet's center. Scientists can determine how far these seismic waves travel in order to reach the Martian core and the speed at which they travel through the Martian interior. This data allows them to estimate the size of the core. And the system's cost effective because it supplements the limited seismic access to planetary bodies beyond Earth. Remember, there's just a single seismic station on Mars, and there were only ever 4 seismic stations delivered to the Moon through the Apollo missions. One of the study's authors, Professor Zuvidi Skulzic from the Australian National University, says the ANU's technique provides an innovative method using a single instrument to scan the interior of a planet in a way that's never been done before.
I've been using seismology to study the core of our planet in the first place, but recently we have published a paper that is basically showing a way forward how to study other planets' cores. And we have an example in that paper on how to use seismology to study the Earth data and the Earth's core, but also the Mars core. And just to clarify, it's a seismology that is different from seismology 10 years ago. And there are 2 particular aspects of this new way that we proposed, or new method that we developed. And the first one is that instead of direct seismic waves that are generated in earthquakes and explosions, we use the late part of the waveforms, several hours after the origin time of large earthquakes. So at the first glance, they don't look useful, right? So they are just tiny wiggles. But instead of looking at the signals, we look at the similarity between these signals. So in mathematics, this is known as cross-correlation.
Are these aftershocks or are these reflections of the initial shock waves, the S&P waves?
They are basically the so-called coda waves, which are reverberations of what you call the direct P and S waves.
Yeah.
So they basically reverberate many hours after an earthquake happens. And
so they're bouncing off different structures, different densities in the planet's interior.
Correct. So they bounce off the internal boundaries and heterogeneities. And basically the similarity that we see recorded on a large number of receivers or seismographs is telling us more about the internal structure than what we get from direct waves. So the similarity between these weak signals turns out to be more prominent information than the signals themselves.
Are they harder to read because they're weaker?
Yeah, basically they're almost invisible, and you wouldn't see them on the seismogram unless you perform the cross correlation, or basically the measure of similarity between these waveforms. And then the signals that come from that become really prominent and tell us something about the internal structure of the planet. But that's not all, right? So that's just the first aspect of this method. The second is another mathematical trickery, I would say, where you replace the sources with the receivers. So in other words, instead of using one large earthquake and many hundreds and even thousands of receivers that we have these days on our planet's surface, you basically replace them, and the earthquake itself becomes a virtual receiver, and many receivers become virtual sources. And when you think about it, it is this reciprocity principle just tells us that it doesn't really matter if waves propagate from point A to point B or from point B to point A. They should see the same structure. And maybe this is not that significant on Earth, but when applied to Mars, it becomes really important because we have a single receiver or a single seismograph on the Martian surface. So that receiver or InSight sensor became our virtual source. And all Marsquakes that were recorded became our virtual receivers.
You're basically reversing the maths in the thing.
Yes. So it's a mathematical trickery where you just replace the location. But when you think about it, the result that you're going to get about the structure is exactly the same. And this was a practical problem that in theory it should work, but in practice it doesn't work that well. So in this new paper, we basically showed the ways to get around it and to make it work. And we first showed how it worked on Earth data, and then we applied it to Martian data from InSight. And you can see why it becomes important because we have a single receiver on Mars. I must say we are very fortunate that we recorded thousands of Marsquakes. And this is beyond expectations, I think, and even we didn't expect that it would work for so long in the first place. So I think it's really great news for the planetary community and people interested in the planetary interiors because it shows the way how these future missions should look like. And I think our method itself is promising because it basically relies on a single instrument that can be placed on the surface of any planet. And the only requirement is that the planet is geologically alive, right? So that it either has earthquakes or quakes or meteorite impacts. So we can use both in this method to work.
And of course, Mars isn't the only planetary body that has seismometers on it, other than the Earth, of course. I'm talking about the Moon.
Yes, absolutely.
It's a differentiated body. We might not call it a planet, but it fits many of the criteria.
Yes, and I'm aware of several missions that are planned for the Moon. We did have data, as you know, from the 1970s, from the Apollo missions, but that was a time that the instruments were not yet broadband and they were not as modern as today. So we are looking forward to these new missions, and my understanding is that several seismometers will be installed on the surface of the Moon.
And is that where you see the next test for this technique?
Absolutely, yes. We would, had it not been for these short period instruments that didn't actually record continuing waveforms. We basically have recording from moonquakes, but not a long time after they happened, right? So for our method to work, we need a continuous recording. And so we are very much looking forward to testing our method on the Moon. And this is going to be definitely the first body, right, planetary body on which we will be able to test the method.
That's Professor Huvedi Skulzic from the Australian National University. And this is SpaceTime. Still to come, evidence for a massive Martian mega tsunami which flooded vast areas of the red planet's northern hemisphere. And later in the science report, promising results from a phase 1 clinical trial of a new HIV vaccine. All that and more still to come on SpaceTime. Okay, let's continue with our Mars theme. Scientists believe a Martian mega tsunami, which flooded a vast area of the red planet's northern hemisphere billions of years ago, may have been caused by an ancient asteroid collision similar to the Chicxulub impact on Earth. The Chicxulub crater is a massive impact structure across Mexico's Yucatan Peninsula and stretching deep out into the Gulf of Mexico. It's the impact point where a 10-kilometre wide asteroid slammed into the Earth 66 million years ago, triggering one of the planet's greatest mass extinction events, the KT Boundary Event, which wiped out some 75% of all life on Earth, including all the non-avian dinosaurs. Now, a new study published in the journal Scientific Reports has provided evidence suggesting a similar-sized impact event occurred on Mars 3.4 billion years ago. Previous research had already proposed the idea of an asteroid or comet impact hitting the ocean in what is now the Martian northern lowlands may have caused a mega tsunami around 3.4 billion years ago. However, prior to this study, the location of the resulting impact crater was unclear. Now, Alexis Rodriguez and colleagues analysed maps of the Martian surface created by combining images from previous missions to the planet and identified an impact crater that could well have caused the mega tsunami. The crater, which they've named Foal, has a diameter of around 110 kilometres and is located within an area of the northern lowlands which previous studies have suggested may well have been covered by an ocean, the impact point being around 120 metres below Martian sea level. The authors suggest that Foal may have been formed 3.4 billion years ago based on its position above and below rocks previously dated to this time period. They simulated asteroid and comet collisions with this region in order to test the type of impact which could have created Foal and whether it could have led to a mega tsunami. The simulations showed that craters similar to Foal would have been caused by either a 9-kilometre wide asteroid encountering strong ground resistance, releasing around 13 million megatons of TNT energy, or a 3-kilometre wide asteroid encountering weak ground resistance, releasing about 500,000 megatons of TNT energy. Now, by comparison, the amount of energy released by Russia's Tsar Bomba, the most powerful nuclear bomb ever tested, was equivalent to approximately 57 megatons of TNT. Both simulated impacts formed craters measuring around 110 kilometres in diameter and generated mega tsunamis that would have reached as far as 1,500 kilometres from the centre of the impact site. Analysis of the mega tsunami caused by a 3-kilometre asteroid impact suggests that the tsunami itself would have measured up to 250 metres tall on land. The authors suggest that the aftermath of the proposed Foal impact may have had similarities to the Chicxulub impact on Earth, which previous research had suggested occurred within a region 200 metres below sea level, generating a crater with a temporary diameter of 100 kilometres and led to a mega tsunami that was some 200 metres high on land. The debris and firestorms it generated created an impact winter which spread around the planet, destroying life and changing the world forever. This is SpaceTime. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more SpaceTime, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.